Hello grade 12s and welcome to question number 7 of the November 2021 Physical Science Paper 2 exam. This question deals with acids and bases. Displayed to the top right hand corner of your screen, you can see table 2 from your formula sheet. The first 5 formulae you should already know from grade 10. We know that N, small n, is for number of mole measured in moles. M is for mass measured in grams. Capital M is for molar mass measured in grams per mole. On the right hand side, we have number of mole as well. Capital N is for number of particles, and Na stands for Avogadro's number, which you actually don't need to know off by heart because it is in table 1, the table of physical constants. Then we have a formula for concentration. In fact, we have 2 formulae for concentration. And here we are speaking about the concentration normally of aqueous solutions. So we say concentration is number of mole divided by volume, or we can say the mass in grams divided by molar mass in grams per mole multiplied by volume, where volume would be in decimeters cubed. Remember, you can have concentration of aqueous solutions and gases, so you can use this formula for either type, but normally we use these formulae for aqueous solutions. Then we have the formula on the right hand side, which is number of moles is equal to volume divided by the molar gas volume. What is very important about this formula is that we only use it for gases. And I sometimes find that learners try to use this formula for aqueous solutions. Please be very careful. These volumes refer to the volumes of gases. Now, below these 5 formulae that you learned about in grade 10, we have a formula that we can use for titrations. Remember that in this formula, the number of mole of acid and the number of mole of base is obtained from the balanced chemical equation. We have a formula that we can use to calculate pH. We say the pH is the negative log of the concentration of the hydronium ions. And then we have the formula for the ionization of water. This is the ionization constant, which is equal to the concentration of the hydronium ions multiplied by the concentration of the hydroxide ions. This is a constant at 298 Kelvin. And it is a constant of 1 times 10 to the negative 14. This is a constant and therefore it does not have any SI units. So now we can go along to question number 7 and see what it says. Question 7.1 says, sulfuric acid H2SO4 ionizes into 2 steps as follows. Number 1, we have that the sulfuric acid will react with water in order to form the hydrogen sulfate ion and the hydronium ion. If we look at this reaction, we see that the sulfuric acid behaves as an acid because it is one. The water acts as a base. An acid is a proton donor, a base is a proton acceptor. Then what happens is that when the sulfuric acid loses its hydrogen ion, it forms the conjugate base, right, where the conjugate base is the hydrogen sulfate ion. When the water gains the proton, it forms the conjugate acid of water, which is the hydronium ion. So this is the conjugate acid. We see that for this reaction, the Ka value, which is the ionization constant, is equal to 1 times 10 to the power of 3. If we write this out in standard notation, it is equal to 1000, and this is a constant. If we look at step number 2 or equation number 2, we see that the hydrogen sulfate ion now reacts with water in order to form the sulfate ion and the hydronium ions. For this reaction, we see that the hydrogen sulfate ion is going to lose its hydrogen, therefore it is behaving as an acid. The water is once again behaving as the base. The conjugate base of the hydrogen sulfate is the sulfate ion. The conjugate acid of the water is the hydronium ion. And we see that the Ka value for this equation is 1 times 10 to the power of negative 2, which in standard notation is just 0,02. Question 7.1.1 says, define an acid in terms of the Lowry-Bronsted theory or Lowry-Bronsted theory. You learned about this theory in grade 11 already, so I do hope that you know it off by heart. We say that an acid is a proton donor, or you can say it's a hydronium ion donor or a hydrogen ion donor. But the most common way of stating this definition is that an acid is a proton donor, and for writing that down, you will obtain 2 marks. Question 7.1.2 says, write down the name or formula of the substance that acts as an ampholyte in the above equations. Give a reason for your answer. We know that an ampholyte is a substance that can act as either an acid or a base. And the first type of ampholyte that we normally learn about in physical science is water, because water is a really good ampholyte. But if you look at these reactions, you will see that in both cases, in step number 1 and in step number 2, water is acting as a base. There is, however, another substance that first acts as a base and then acts as an acid. This substance is the hydrogen sulfate ion, and therefore the hydrogen sulfate ion in these equations is behaving as the ampholyte. So for 1 mark, we write down either the name or the formula of the hydrogen sulfate ion. That gets us 1 mark. And the reason why we are saying that this is the ampholyte in the above equations is that it acts as a base in reaction number 1, and it acts as an acid in reaction 2. This will get you a mark. If you instead just said it acts as an acid and a base, you will also get your mark for the reason. And this gets you your 2 marks for question 7.1.2. Question 7.1.3 says, the conductivity of solutions of hydrogen sulfate ions and sulfuric acid are compared. Which solution will have a lower conductivity? Explain the answer. So when we have ions dissolved in solutions, or ions that have been dissolved in water, we know that these solutions will be more conductive if there is a high concentration of ions in the solution. If there's a low concentration of ions in the solution, then the solution will be less conductive. So if we go all the way up to step number 1 and step number 2, you'll soon notice that step number 1 is a solution, or shows the sulfuric acid being dissolved in water. And they told us that the Ka value, the ionization constant for this reaction, is 1000. 1000 is a much bigger number than 1. It is a value far greater than 1. Therefore, we know that sulfuric acid is a strong acid. And what is the definition of a strong acid? It is an acid or a substance that will ionize completely in water. So we know that when the sulfuric acid dissolves in water, a high concentration of hydrogen sulfate ions and hydronium ions are going to form, and therefore there's going to be many ions present in the solution, allowing the conductivity to be very high. But if we look at the second step, here we have taken the hydrogen sulfate ions and dissolved them in water to form ions, sulfate, and hydronium. The Ka value here is 0,02. This number is smaller than 1. Ka is the ionization constant of an acid. So since this value is smaller than 1, we know that the hydrogen sulfate ion is a very weak acid, and it will not ionize completely in water. It will ionize to form only a few or very little of these ions in water. So therefore, grade 12s, we know that the answer to question 3.1.3 is the hydrogen sulfate ions, or rather the hydrogen sulfate solution. So since this question is out of 3 marks, we know that we're going to get 1 mark for writing down the hydrogen sulfate ions. And the other 2 marks, since this question is out of 3 marks, will be awarded for giving valid points, 2 valid points as explanation. Point number 1, we say that the smaller Ka value is given, or rather the HSO4 minus ion solution has the smaller Ka value, and it is therefore a weaker acid. The second mark we get for saying that this means that there will be a lower ion concentration, or we say it is incompletely ionized. Any of these will do, and that is going to get you your 2 other marks, giving you a total of 3 marks for this question. Question 7.2 says, the pH of a hydrochloric acid solution, HCl, is 1,02 at 25 degrees Celsius. Calculate the concentration of HCl. We know that HCl in solution is going to ionize. So if we place it in the presence of water, it will ionize. It ionizes because it is covalently bonded. And we then end up with chlorine ions and hydronium ions. This chemical equation is already balanced, and the ratio of hydrochloric acid to the amount of hydronium ions formed is 1:1. Since we know the pH, we would like to use the pH value in the pH formula to calculate the concentration of the hydronium ions. Because if we can calculate the concentration of the hydronium ions, then we will know the concentration of the HCl solution. So, how do we calculate pH? We go to the formula sheet and we see pH is equal to negative log the concentration of H3O plus. We know that the pH is 1,02, so we substitute that value into the formula. Now, in order to solve for this concentration, step number 1 is to divide by the negative, so that we get negative 1,02 is equal to log H3O plus. Into your calculators, you will now press Shift Log and enter negative 1,02, and then you find out that the concentration of the H3O plus is equal to 0,0955 mole per decimeters cubed. Very often, when learners write down the SI unit for concentration, they write this to the power of positive 3. Please remember, we are dividing by volume. When we calculate concentration, it is number of mole divided by volume. So it is mole per decimeter, where on the decimeter needs to be a negative 3. So we now know the concentration of the hydronium ions, but we know that HCl to the number of moles of H3O plus that forms is 1:1 according to this balanced equation. Therefore, we know that the concentration of the HCl is going to be equal to the concentration of the hydronium ions, and it is therefore also 0,0955 mole per decimeter cubed. If you round this value off, then you get 0,10 mole per decimeters cubed. It's up to you if you'd like to round it off. We can leave it in its form, or we can round off and you will get full marks. But please remember that you should not round off in between. So this answer should not be rounded off. In this question, you're going to get 1 mark for your formula for pH, 1 mark for substituting into this formula the pH value, 1 mark then for calculating the concentration of the hydronium ions, which is equal to the concentration of the hydrochloric acid solution. Question number 7.2.2 begins with some new information. It says this hydrochloric acid solution. When they say this hydrochloric acid solution, they are talking about the one that we just performed a calculation for, whose concentration is equal to 0.096 mole per decimeter cubed. Now they say that this hydrochloric acid solution reacts with sodium carbonate, Na2CO3, according to the following balanced equation. 50 centimeters cubed of the hydrochloric acid solution is added to 25 centimeters cubed of a 0.075 mole per decimeter cubed solution of sodium carbonate. 7.1.2 says, calculate the concentration of excess hydrochloric acid. The word here, excess, is incredibly important. It tells us already that the hydrochloric acid is in excess, and therefore the sodium carbonate is the limiting reagent. So if we're looking for the excess hydrochloric acid, we're trying to find out firstly how many moles of hydrochloric acid did not react and is therefore in excess. Once we know the number of moles of hydrochloric acid that is in excess, we can use it to calculate the concentration of the hydrochloric acid that is in excess. So let's start off by determining the number of moles of the limiting reagent. We say number of moles of the sodium carbonate. Please remember, you must include labels so that you don't confuse the marker. Make it easy for markers to mark your work. The volumes here are given in centimeters cubed. I'm going to go ahead and convert it to decimeters cubed by dividing by 1000. So 25 centimeters cubed is equal to 0.025 decimeters cubed. So we're now going to say 0.075 multiplied by 0.025 decimeters cubed. In the end, the number of moles of the limiting reagent is equal to 0.01875 mole. And please remember, we only round off right at the end. Now, how many mole of the hydrochloric acid did we start off with right at the beginning? Let's calculate that. The number of moles of hydrochloric acid in the beginning, so I'm using the term initial, the I is for initial, is again equal to C multiplied by V. The concentration of the hydrochloric acid we calculated in the previous question to be 0.096. Here I'm actually using this answer, but rounded off over there to 96. Okay, so don't get confused. That is the concentration that I'm using. We're going to multiply this by the 0.05. And we end up with an answer that is equal to 0.00475 mole. This is the number of mole of HCl that we started off with. Now let's find out how much of this hydrochloric acid actually reacted with the limiting reagent. To do so, we're going to make use of the stoichiometric ratio and this number of moles. The ratio of HCl to sodium carbonate is going to be 2:1. That means that the number of moles of HCl that actually reacted is going to equal to 2 times 0.001875. When we plug this into our calculators, we find out that the number of moles of HCl that reacted or was used up is going to equal to 0.0038 mole. So now we know the number of mole of HCl that we started off with, and we know how much of it was used. We can use these two values to calculate the number of moles of HCl that is in excess. We say the number of moles of HCl that is in excess is going to equal to the initial number of moles minus the number of moles that was used. So that is going to equal to 0,00475 minus 0,0038. When we plug this into our calculators, we end up with an answer of 0,00095 mole. This is the number of mole in excess. We are looking for the concentration in excess. To calculate concentration, we say concentration of HCl, of course, is equal to number of moles divided by volume. We know that the number of moles in excess is going to equal to 0,00095. But what is the volume going to be? Well, remember, we have now mixed two solutions together, a 0,05 decimeter cubed solution and a 0,025 decimeter cubed solution. The new volume here is therefore 0,075, where we have added these volumes together to obtain the new volume. In the end, the concentration that we obtain is going to be equal to 0,013 mole per decimeter to the negative 3, of course, and this is the final answer to this question. You're going to be awarded marks as follows. Number 1, you're going to get a mark for your formula. Number 2, a mark over here for substituting. A mark for your method of calculating the initial number of moles. A mark for your method of calculating the number of moles that actually reacted or was used up. You're going to get 2 marks for calculating the number of moles of HCl in excess. That is 2 marks. Unfortunately, they don't indicate where or whether or not. No, they do indicate. I do apologize. Both of these marks are awarded for the workings, alright? So your workings need to be correct. Then, grade 12, you're going to get 1 mark for dividing by the correct volume, 0,075, and your final mark for this question out of 8 marks you get for the final answer. This is a very long question, and you can work it out using first principles as I have, or if you would like to, you can make use of this formula on your formula sheet. This is the formula that we normally use for titrations. CaVa over Cb Vb is equal to Na over NB. You're welcome to try and use this formula, and of course when you are done, go and have a look at the marking guidelines to see if you have answered this question correctly, to see if your method is correct. But this brings us to the end of this question number 7 on acids and bases. In the end, this question is out of 18 marks. In the next question, we're going to be dealing with electrochemistry. Specifically, we will start off with galvanic cells when we look at question number 8.